Hello everyone, my name is Elias Mariel and with me is Daniel Ålund. We are going to present some of the test methods that have been developed as part of Trust Vehicle at Volvo Cars. And mostly we're focusing on ways to quantify sensor availability during cleaning and critical scenarios. The methods that we're looking at today focus mainly on ways to evaluate performance in harsh weather conditions, the safety, availability, and reliability of the sensor input to the function, as well as function performance due to sensor input during critical scenarios. As a proof of concept for the methods, we used two different test vehicles, one focusing on comparing the availability of different mounting locations, where we have one sensor mounted on the roof and two in the grill at different offsets. And then we have another test vehicle that's more focused on the cleaning and contamination methods. We evaluate the methods both on test track measurements at our proving ground in Helleret, near to Gothenburg, as well as in real public road conditions on the 80 certified driving route around Gothenburg city center. Now, the first method that we're going to describe today was developed to evaluate the blockage of sensors during cleaning activation. For this, we use LiDAR data, and we wanted to provide a general method that can be used with any LiDAR sensor, so it's not focused on a specific LiDAR technology. This method uses a voxel-based 3D convolutional neural network that outputs an object classification, which was developed as part of a thesis project for Volvo Cars a few years back. Along with the classification, we also look at the number of detections and average reflectivity measured from the target. And the training input for this method is from various data sets that are publicly available. The proof of concept for this method was to investigate the impact of foaming on glass surfaces. So here we have water activation from standard cleaning nozzles on glass surface, and we compare that with normal European washer fluid to take a look at the impact of the foaming on the glass. We did stationary measurements with various targets where we activate the cleaning. First, it's the three furthest left nozzles and then the three furthest right nozzles. So here we see that with water, we have a small impact on the classification. Here we are comparing the output of the convolutional neural network to the vehicle class. So if we classify it as a vehicle, the score is 1. If it's classified as some other class, it will be 0. So we see that we only lost the classification for 0.1 seconds. And if we compare that to washer fluid activation, we see that we lose the classification for about 5 seconds, or 5.5 seconds in this case. And it's about 3.7 seconds after the cleaning is actually stopped that we get a stable classification back. We also developed a method for evaluating rain, snow, and aerosol in the actual air, trying to separate that from water gathering on the fascia of the car. So here we have a prototype mock-up of a fascia of a car, and we apply hydrophobic film to one side of the sensor field of view, and we don't have a film on the other side. So with this, we can separate the impact of the water that's gathering on the fascia of the car. And during public road testing, this allows you to evaluate the effect of the raindrops, snowflakes, and aerosol without being impacted by the water on the lens. And to validate this, we actually did some test track measurements comparing the POD, or probability of detection, in rainy condition with and without the hydrophobic film. And we see that there is an improved consistency in probability of detection with the film. So with this method, it allows you to go out and collect data and evaluate just the impact of the airborne particles. And I'll hand it over to Daniel.
Thank you, Elias. Method for evaluation of sensor availability in critical scenarios. To evaluate sensor availability in critical scenarios and how it impacts the safety of the function, a test scenario from Euro NCAP was used. This specific scenario partly or completely obstructs the pedestrian at a given position, which limits the time to act and gives the critical scenario. The test scenario used was the car to pedestrian near side adult. Sensor position on the car will in this scenario have a big impact on the total time where the VRU can be detected and the decision to react can be taken. 3 sensor positions are used, 2 at the grille and 1 on the roof. Here we see the critical scenario from different point of views. The picture to the right shows the distribution of points in bins over Z-axis during the time span of the scenario. This log was recorded at 10 Hz, which means that 10 frames equals 1 second. Red is the lowest amount of detections and dark blue is 50 detections and above. Each square is approximately 10 centimeters in height. The dotted line is the frame where the pedestrian is directly in front of the vehicle. The reason why we are missing points on the top 2 graphs is because we are almost in collision with the target, thereby reaching the minimum sensor range. This gives a clear overview of how the availability of the sensor is depending on the mounting position. Methods for quantifying availability of sensors during cleaning and critical scenarios. 3 methods were developed to evaluate different aspects of sensor availability with the aim of improving robustness and safety of function that make use of the sensor data. The impact of sensor blockage during cleaning activation can be evaluated with a generalized method, but the algorithms used must be chosen with the sensor technology in mind. To understand the impact of rain, snow, and aerosol in the sensor's field of view, a method to emulate an ideal cleaning solution is required. Using the EuroNCAP car to pedestrian near side adult is a good way of evaluating sensor availability in this specific critical scenario. A combination of the shown methods can be used to evaluate the sensor availability in a critical scenario with adverse weather conditions. Thank you.